January 1942. Boeing's Seattle plant was supposed to be America's answer to the Luftwaffe. Instead, the massive factory looked like a monument to failure. 63 B-17 flying fortresses sat incomplete on the assembly line, each one a broken promise. The Army Air Forces had ordered 3,615 bombers for the year. Boeing had delivered exactly 9 aircraft, not 90, not 900, 9. General Henry Hap Arnold wasn't disappointed when he found out. He was absolutely furious. In a heated meeting on January 15th with Boeing executives, Arnold made the stakes brutally clear. Without bombers, there would be no strategic bombing campaign against Germany. Without strategic bombing, American soldiers would face an entrenched Nazi war machine for years. The mathematics were simple and terrifying for everyone in that room. The problem wasn't workers or raw materials like you might expect. Boeing had hired over 30,000 people in just 6 months, many of them women who'd never touched factory equipment before Pearl Harbor. Aluminum was flowing in from Alcoa plants faster than they could possibly use it. The crisis was something nobody anticipated during planning. The bombers themselves were simply too complex to build quickly using traditional methods. Each B-17G required 140,000 individual parts assembled with precision. The wings alone demanded 12,000 rivets per side, connecting 7 overlapping layers of aluminum skin to an internal framework. That framework had to withstand stresses up to 6 G-forces during combat maneuvers, without failing. Traditional assembly methods perfected on smaller aircraft just collapsed under this overwhelming complexity. Philip Johnson, Boeing's production manager, walked the factory floor every morning at 5 a.m. with clipboard in hand. He watched the same nightmare unfold day after day. Wing Assembly Station Number 4 had 17 workers clustered around a single wing section, like bees on a hive. They were constantly getting in each other's way, stumbling over tools and air hoses. One riveter would finish a seam and step back. Another would immediately need to access that exact spot for a different rivet line. Then a third worker needed that same position for yet another line of rivets. The choreography was absolutely insane, like watching people try to dance in a phone booth. Johnson timed it himself with a stopwatch, 20 hours and 14 minutes to complete one wing assembly from bare framework to final rivet. 20 hours for one wing. Meanwhile, the British were losing bombers faster than that over Germany every single day. Every Luftwaffe fighter that went unchallenged because American bombers weren't in the sky meant more consequences. More merchant ships sunk in the Atlantic. More factories running at full capacity in the Ruhr Valley. More time for Nazi Germany to consolidate its grip on occupied Europe. Boeing's engineers had already tried everything they could think of to speed up production. They'd redesigned tool access points. They'd created specialized jigs and fixtures. They'd even experimented with different crew sizes, thinking maybe fewer workers would somehow reduce congestion on the line. Absolutely nothing worked to solve the fundamental problem. The issue remained stubbornly consistent. The rivet pattern specified in engineering blueprints required work crews to access the same physical space in an overlapping sequence. You couldn't parallelize the work effectively. You couldn't add more workers to speed it up. It was a bottleneck written directly into the aircraft's DNA by the original designers. By late January, Boeing executives were having quiet conversations about the previously unthinkable, telling the Army they simply couldn't meet production targets at all. Some even whispered about bringing in Douglas or Consolidated to take over primary production from Boeing entirely. On January 28th, a classified memo circulated among senior management that nobody wanted to see. The subject line read, "Crisis Assessment, B-17 Program Viability." Nobody wanted to be remembered as the person who lost the war because they couldn't figure out how to rivet aluminum fast enough. Walk into Wing Assembly Station 4 on any given morning and you'd witness organized chaos. Except it wasn't actually organized at all. The wing section lay on a massive jig, a skeleton of aluminum ribs and spars spanning 32 feet, 7 layers of aluminum sheeting weighted nearby, each precisely cut and drilled with thousands of holes. They had to be attached in a specific sequence that made sense structurally but not practically. The process started from the wing root where it would bolt to the fuselage eventually. Workers moved outward toward the tip, following the engineering blueprint exactly. Sounds straightforward when you describe it. It absolutely wasn't in reality. The engineering blueprint specified that rivets had to be installed in rows running parallel to the wing's leading edge. Row 1 first, then row 2, then row 3, marching steadily backward toward the trailing edge in perfect sequence. This pattern made perfect structural sense to engineers in their offices. Each row reinforced the one before it, creating an overlapping shingle effect that distributed stress loads evenly across the wing surface during flight. The engineers at Boeing's development center had calculated every single rivet's position to optimize strength-to-weight ratios. On paper, the design was absolutely beautiful. On the factory floor, it was a complete disaster for production. Here's why the system failed so badly. To install row 1, a riveter worked from the top surface with his pneumatic gun. Meanwhile, a bucker, the person holding the backing bar, worked from below, through the wing's internal structure. They had to be perfectly synchronized in their movements. The riveter's pneumatic gun drove the rivet through pre-drilled holes at 3,000 pounds of force. The bucker's bar pressed against the rivet's tail from the opposite side, shaping molten aluminum into a mushroom head that locked everything together. Miss the timing by even half a second and you got a loose rivet. Loose rivets had to be drilled out completely and replaced, adding 3 minutes per mistake. Multiply that across 12,000 rivets per wing, and mistakes became absolutely catastrophic for the schedule. But the real nightmare started when row 2's crew began their work sequence. To access row 2's rivet line, workers needed to position themselves exactly where row 1's crew had just been working moments ago. Except row 1 wasn't actually finished yet, not completely. Quality inspectors needed to check every 10th rivet with a borescope, a tedious process taking 15 minutes per wing section. So row 2's crew just stood there waiting. Meanwhile, row 3's crew, already suited up and ready to work, stood around burning precious daylight. The production schedule called for parallel work streams to speed things up. But the physical reality of the wing's geometry made that approach completely impossible. You simply couldn't fit enough workers around the structure to rivet multiple rows simultaneously without chaos. The rivet guns themselves created another serious problem for coordination. These weren't delicate precision instruments like jeweler's tools. They were industrial pneumatic hammers that shook your entire body when fired repeatedly. The compressed air hoses snaked across the factory floor like demented pythons, constantly getting tangled with electrical lines for the inspection lights, tripping workers who were trying to move between stations. One riveter moving from position A to position B had to unplug his air hose first, coil it up carefully, walk around 3 other workers, find a new air coupling station, plug back in, then resume work. That 30-second process happened 70 times per wing section, wasting hours daily. Then there was the heat problem that nobody had predicted. Seattle in January wasn't warm outside, but the factory was sweltering. 17 workers clustered around one wing section, each generating body heat, each pneumatic gun adding more warmth to the enclosed space. The aluminum sheeting absorbed that heat and expanded microscopically, just 0.003 inches per 10-foot section. But when you're trying to align pre-drilled holes that have 0.002-inch tolerances, that expansion meant holes didn't line up anymore. Riveters spent 15% of their time using tapered reamers, enlarging holes that had shrunk out of alignment as the metal cooled. None of this appeared in the engineering specifications because nobody had anticipated 17 people working in such close proximity for such extended periods under these conditions. Frank Szymanski didn't look like someone who'd changed the course of world history. He was 31 years old, 5'7", with hands permanently stained with aluminum dust and cutting oil from constant work. Before Pearl Harbor, he'd worked at a Chrysler plant in Detroit installing door panels on Windsor sedans. Repetitive work, mindless work really, the kind of job where your hands knew what to do before your brain caught up. When Boeing started hiring in late 1941, Frank moved his wife and 2 daughters to Seattle, took a room in a boarding house near the plant and joined the swing shift at Wing Assembly Station 4. He started work at 4 p.m. and finished at midnight 5 days weekly, sometimes 6, when production quotas demanded overtime. What made Frank different wasn't his riveting skill particularly. Dozens of workers could match his speed and precision with the pneumatic gun. What made him different was that Frank couldn't stop watching the entire process unfold. Most riveters focused exclusively on their immediate task right in front of them. Line up the gun, squeeze the trigger, move to the next rivet, repeat 400 times per shift. Frank saw the entire ballet of movement across the whole wing assembly. He noticed that Jenkins working row 3 was always waiting for Patterson to finish row 2. He noticed Patterson was always waiting for quality control to clear row 1. He noticed the sequence created a cascade of delays that compounded geometrically as you moved across the wing surface toward completion. On February 4th, during a midnight break, Frank sat on an overturned parts crate, eating a bologna sandwich. He stared at a completed wing section being moved to final assembly, and something about it bothered him deeply. The rivet pattern looked structurally perfect from an engineering perspective he could see. Each row overlapped the previous one, creating that shingle effect the engineers loved to talk about. But Frank kept thinking about his old job at Chrysler before the war. When they installed door panels on cars, they didn't start at one edge and work across linearly. They started at 4 corners simultaneously and worked toward the center from multiple directions. Why did they do it that way? Because it let 4 workers operate in parallel without ever getting in each other's way. The geometry of the door panel made parallel work possible and efficient. He looked back at the wing schematic posted on the station's bulletin board for reference. The rivet pattern ran in perfectly straight lines from leading edge to trailing edge. Parallel rows marching across the wing surface in military precision. But the wing itself wasn't actually a flat rectangle like a door panel. It was a complex 3-dimensional structure with depth, with internal ribs creating separate chambers, with access points at very specific locations determined by the wing's shape. What if the rivet sequence matched the wing's actual geometry instead of treating it like a flat sheet? What if you started at multiple points simultaneously? Points chosen because they gave workers maximum physical access without any overlap. Frank grabbed a pencil and started sketching on the back of his time card. Instead of straight rows, he drew a pattern that looked almost random to the eye. Rivets clustered densely around structural ribs where access was easiest. Then, radiating lines connecting those clusters, following the natural contours of the wing's internal structure rather than fighting against them. It looked wrong when you first saw it. It looked like someone had spilled rivets on the blueprint and decided to leave them where they fell by accident. But as Frank traced the pattern with his finger following the lines, he realized something crucial. You could have 5 workers riveting simultaneously without any of them needing the same physical space at the same time. Worker 1 could be at the wing root inside the main spar chamber. Worker 2 could be mid-wing accessing through the inspection panel. Worker 3 could work the trailing edge, which was shallow enough for top-down riveting without needing a bucker. They'd never intersect physically. They'd never wait for each other. The structural implications worried him when he thought about it. The engineering blueprint specified that parallel row pattern for serious reasons. Load distribution, stress concentration, technical terms Frank only half understood from conversations. But he kept thinking about something else he'd noticed during months of work. Rivet failures almost never happened where 2 rows met in the standard pattern. They happened at transition points where the wing skin changed thickness or where cutouts for fuel tanks interrupted the pattern. The rows themselves weren't magical structurally. They were just one way among many to distribute fasteners across the surface. Maybe not the only way that would work. Frank knew exactly what would happen if he walked up to a production supervisor with his sketch. They'd smile politely, tell him the engineers had spent months calculating those rivet positions, send him back to his station to keep working. The hierarchy in Boeing Plant 2 was absolutely rigid and unforgiving. Engineers designed aircraft, supervisors managed production, workers assembled parts. Nobody expected innovation from a guy whose official job title was Riveter Grade 2. But Frank had one significant advantage working in his favor. He worked swing shift, and swing shift supervisor Bill Hendricks was genuinely different from other managers. Hendricks had started as a sheet metal worker himself before being promoted to supervisor in 1940. He actually listened to floor workers, which made him either remarkably progressive or dangerously naive depending on who you asked in management. On February 11th, Frank caught Hendricks during the 8 p.m. shift change and showed him the sketch. Hendricks stared at it for a long time without speaking. Then he said something Frank hadn't expected to hear. "This violates every structural loading principle Boeing uses. You know that, right?" Frank nodded slowly. He knew, or at least he suspected as much. Hendricks kept talking while examining the sketch. The parallel row pattern isn't arbitrary decoration. When the wing flexes under load during flight, stress concentrates along predictable lines. The rivet rows are positioned perpendicular to those stress lines. That's foundational stuff taught in every aerospace engineering textbook published since 1927. The principle Hendricks was describing came from work done by Theodor von Karman and his team at Caltech in the late 1920s. They'd proven mathematically that fastener patterns in load-bearing structures needed to follow stress trajectories, the invisible lines of force that flow through metal under pressure. The bottom surface was under tension, trying to stretch. The top surface was under compression, trying to compress. Right along the middle, the neutral axis, stress approached zero. Von Karman's equations showed that fasteners needed to be densest where stress was highest, and could be sparser where stress was minimal for efficiency. The parallel row pattern achieved this optimization perfectly on paper. Each row corresponded to a specific stress magnitude, with rivet spacing calculated to match load requirements precisely. Frank's pattern threw all of that careful calculation out the window completely. His clusters placed dense rivet concentrations around structural ribs, not stress lines. His radiating connections followed access convenience, not load paths calculated by engineers. From a classical engineering perspective, it was complete gibberish that made no sense. The wing might hold together during taxi tests, might even survive the first few flights without problems. But under sustained combat stress over Germany, microfractures would develop where the rivet pattern failed to match the stress pattern. Those fractures would propagate through the aluminum. The wing would fail catastrophically. Men would die over enemy territory. Hendricks explained all of this to Frank on the noisy factory floor, shouting over the constant pneumatic guns. Then he asked a question that changed everything about how they thought. But did von Karman ever consider assembly efficiency as a structural factor in his calculations? Frank looked confused by the question. Hendricks continued his thought. If it takes us 20 hours to rivet a wing and we make mistakes because workers are exhausted and cramped and tripping over each other, how many of those 12,000 rivets are actually installed to specification? How many are slightly loose because the bucker missed his timing by a fraction? How many holes are slightly reamed because they didn't align perfectly due to heat expansion? He paused to let that sink in. Your pattern might be theoretically weaker on paper, but what if it produces practically stronger wings? Because the installation quality is absolutely perfect every single time. This was heresy in Boeing's engineering culture. Quality control processes assumed that workers followed procedures correctly by default. The procedures were designed around the engineering specifications that came from the top. If wings were failing quality checks, you retrained workers or fired them and hired better ones. You didn't redesign the aircraft to accommodate worker limitations and human factors. That was backwards thinking. That was letting the tail wag the dog. But Hendricks had seen something in his 3 years as supervisor that engineers in their offices hadn't. He'd seen that theoretical perfection and practical reality diverged more than engineers wanted to admit to themselves. He'd seen riveters so exhausted by hour 18 of a wing assembly that their hands physically shook. He'd seen buckers miss their timing because they'd been crouched in the same uncomfortable position for 40 minutes and their legs cramped up. He'd seen quality inspectors approve marginally loose rivets because rejecting them would mean another 2-hour delay, and production quotas were already impossible to meet. What if Frank's impossible pattern, by reducing assembly time and worker fatigue, actually produced more reliably perfect installations? Hendricks folded Frank's sketch carefully and put it in his pocket. "I'll talk to someone who might listen," he said. Frank went back to his rivet gun expecting absolutely nothing to come of it. Hendricks didn't go to the chief engineer like protocol demanded. That would have been career suicide. Oliver Eccles, Boeing's head of engineering for the B-17 program, had a legendary reputation for eating floor supervisors who questioned his designs. Instead, Hendricks went to Donald Douglas, no relation to the aircraft company, who was assistant production manager, and who was also 3 weeks away from being fired if production numbers didn't improve dramatically. Douglas was desperate enough to listen to crazy ideas from anywhere. On February 18th, Douglas looked at Frank's sketch for about 30 seconds before saying flatly, "This is garbage. Get it out of my office immediately." Hendricks didn't move or leave. He pulled out his notebook and showed Douglas something else, assembly time logs from Wing Station 4 over the past 6 weeks. Every single wing had taken between 19 and 22 hours to complete. Not a single outlier, not one crew that figured out how to go faster despite trying. The bottleneck was structural, built permanently into the process itself by the design. Douglas looked at the numbers, then back at the sketch in silence. Even if this works from an efficiency standpoint, Eccles will never approve it. Never in a million years. He'd rather shut down the entire plant than rivet a wing in a non-standard pattern. Here's what Douglas understood that Hendricks didn't know. Boeing was literally weeks away from losing the B-17 contract entirely to competitors. Consolidated Aircraft had been lobbying the Army Air Forces hard, arguing that their B-24 Liberator was easier to manufacture and could be produced in dramatically higher numbers than the Fortress. General Arnold was listening carefully to those arguments. If Boeing couldn't demonstrate dramatic production improvements by March 15th, the Army would redirect orders to Consolidated and other manufacturers. Boeing would keep some production, but they'd lose their position as America's primary heavy bomber supplier forever. That meant massive layoffs across Seattle. That meant the city's economy collapsing. That meant Douglas losing his job anyway, so what did he have to lose? Douglas made a decision that violated about 17 different Boeing protocols and procedures. He authorized a test without formal engineering approval, but he couldn't do it during day shift when senior management was walking the floor. He couldn't do it on swing shift because too many people would see and ask questions. He scheduled it for graveyard shift February 21st, starting at midnight, when the plant was nearly empty. He pulled a wing section that had already failed quality control for unrelated reasons, a damaged spar that made it unsuitable for flight anyway. So if the test went catastrophically wrong, they weren't wasting a perfectly good wing on an experiment. He assigned Frank and 4 other riveters, all swing shift veterans who'd volunteered without being told exactly why. And he told absolutely nobody else in management what they were about to attempt. The test began at 12:14 a.m. with 5 nervous workers. Frank had spent 3 entire days refining his pattern, working out exactly which rivet clusters went where, calculating sequences that would let all 5 workers operate simultaneously without coordination. He'd color-coded the blueprint for clarity. Red for worker 1, blue for worker 2, green for worker 3, yellow for worker 4, purple for worker 5. Each color represented a physical zone that didn't intersect with any other color zone geometrically. The workers could literally rivet at the same time without coordinating, without waiting, without bumping into each other at all. It looked absolutely insane watching it happen in real time. Traditional riveting had a rhythm, a sequential logic that made sense visually. This looked like controlled chaos, or maybe just chaos. One worker was inside the main spar cavity, another was underneath the trailing edge. A third was working topside near the leading edge. They weren't following rows in any recognizable pattern. They were following clusters that seemed randomly scattered. Douglas stood 30 feet away with a stopwatch, chain-smoking Lucky Strikes nervously. Hendricks stood next to him in complete silence. Every 15 minutes, Douglas checked his watch and wrote down the time on his clipboard. At the 2-hour mark, the wing should have been maybe 20% complete, according to all previous data. It was 45% done instead. The workers were starting to realize something unusual was happening here. They weren't waiting for anything. Not for each other, not for inspectors, not for access to cramped spaces. Every rivet position Frank had marked was genuinely accessible without interference from other workers. The pneumatic hoses weren't tangling because workers weren't crossing paths constantly. The heat buildup was noticeably lower because they weren't clustered in one area. The aluminum wasn't expanding as much because 5 heat sources distributed across the wing surface created less concentrated thermal load than 17 sources in one spot would. At 21 a.m., exactly 127 minutes after starting, the final rivet was installed. Douglas clicked his stopwatch and stared at it. He didn't say anything for a long moment. He just walked up to the wing and started inspecting rivets at random, pulling out his borescope and checking for proper mushroom formation on each one. Hendricks held his breath watching. Frank stood there covered in aluminum dust, trying to read Douglas's unreadable face for any reaction. Douglas inspected 30 rivets before he trusted his own eyes about what he was seeing. Each one was absolutely perfect. The mushroom heads were uniform, properly seated, with no gaps between the aluminum sheets anywhere. He called over Jimmy Chen, the graveyard shift quality inspector, without explaining what he was looking at or why. Chen grabbed his toolkit and started a full inspection protocol, the exact same one he'd run on 200 previous wings in his career. He checked rivet spacing with precision calipers. He used a thickness gauge to verify the sheet metal compression was correct. He tapped each rivet head with a small ball-peen hammer, listening carefully for the solid thunk that indicated proper seating versus the hollow ping of a loose rivet. 40 minutes later, Chen looked up with a confused expression. "This passes inspection. I don't know what crew did this work, but it's clean, really clean." Douglas told him how long it took to rivet. Chen thought he was joking at first, then he thought the stopwatch must be broken. Then he rechecked his entire inspection, because wings that rivet that fast shouldn't be this clean according to all his experience. There had to be mistakes somewhere, rushed work, something wrong. He found absolutely nothing wrong. The wing was perfect. Better than perfect, actually. Chen had been inspecting B-17 wings since July 1941, and he kept a private log of defect rates that he never showed management because the numbers were depressing. The average wing had 140 rivets that needed attention during quality control for various problems. Loose rivets, misaligned holes, installation errors. This wing had exactly 11 problems. 11. Less than 1/10 the normal defect rate. But passing visual inspection didn't mean the wing would actually survive flight loads and combat stress. The rivet pattern was still completely wrong, from a structural engineering standpoint according to all established theory. Douglas knew they needed real testing, the kind that required equipment and authorization he absolutely didn't have. At 3:30 a.m. he made another unauthorized decision that could end his career. He called the night crew at Boeing's structural test facility in Building 7, told them to prepare for an emergency stress test immediately. He didn't mention that the wing used an unapproved rivet pattern that violated all standards. He just said they needed rush testing on a wing section for production validation purposes, making it sound routine. The test facility had equipment designed to simulate flight loads under controlled conditions. A massive hydraulic press could apply up to 150,000 pounds of force to a wing section, bending it upward and downward to replicate the stress of extreme flight maneuvers and combat. The standard B-17 qualification required wings to withstand loads equivalent to 6.2 times the aircraft's maximum weight, without permanent deformation after the stress was removed. That was the safety margin built into military specifications. Army Air Force's Specification R11816B, established in March 1941, mandated this testing for any structural modification to production aircraft under any circumstances. Douglas was about to test a wing that violated R11816B in every possible way, using a facility that wasn't authorized for non-standard testing at 4 a.m. when nobody in authority was watching. They mounted the wing section in the test frame at 4:15 a.m. The hydraulic press engaged with a hiss, applying upward pressure that bent the wingtip skyward slowly. Douglas watched the strain gauges with intense focus. At 1 G equivalent load, the wing flexed normally. At 3 Gs, still completely normal. At 6 Gs, the deflection matched specification exactly as it should. At 6.2 Gs, the qualification threshold required by the military, the wing held without issues. No creaking sounds, no rivet popping, no stress fractures forming visibly in the aluminum skin. Douglas told the operator to keep going past the specification limit. At 7 Gs, the wing was still structurally sound. At 8 Gs, individual rivets near the wing root started showing strain, but that was expected and acceptable. The wing root carried the highest loads and was supposed to be the first failure point by design. At 8.4 Gs, far beyond any possible combat load, the test was terminated. Not because the wing failed, but because Douglas was genuinely terrified of breaking the expensive test equipment itself. They released the hydraulic pressure carefully. The wing returned to its neutral position with no permanent deformation visible at all. Zero deformation. A properly designed wing should show some microscopic permanent set after being loaded to 8.4 Gs according to all theory. This wing didn't show any. It behaved like it had been stressed to maybe 5 Gs maximum. Chen ran his inspection protocol again, checking every rivet that had been under maximum load during the test. None had loosened even slightly. None showed evidence of microscopic slippage or movement. The wing was somehow stronger than wings built to the standard pattern that engineers had calculated so carefully. Douglas stood there at 5:47 a.m., trying to understand what he was seeing that contradicted everything. Frank's pattern had placed rivet clusters around the structural ribs, and those ribs were the primary load-bearing members of the wing structure. By concentrating fasteners where the structure was strongest naturally, Frank had accidentally created a pattern that reinforced the wing's natural load paths, instead of fighting against them like the parallel rows did. The radiating connections between clusters acted like secondary stress distributors, channeling loads away from weak points in the aluminum. It wasn't random at all when you understood it. It was organic. It matched the way forces actually flowed through the structure during flight instead of the way engineers thought they should flow, based on simplified calculations. By 6 a.m. on February 21st, Douglas knew he had to bring this to someone who could actually authorize full-scale implementation. Not Eccles, who would kill it on principle. He went straight to James Murray, Boeing's vice president of operations, waking him up at his home in Laurelhurst at an ungodly hour. Murray arrived at the plant at 7:15 a.m., still in his weekend clothes, and demanded to see everything immediately. The test data, the inspection reports, the time logs, all of it. He watched Douglas's hand shake as he explained what they'd done without authorization or approval. Murray's face was completely unreadable throughout the explanation. Then Murray asked the only question that actually mattered for the company. Can we train 200 riveters to use this pattern by Monday morning? Douglas hadn't thought that far ahead at all. He'd been so intensely focused on proving the concept worked that he hadn't considered scaling it across the entire production line. Murray was already doing the math in his head. If one wing went from 20 hours to 2 hours, and Boeing had 42 wing assembly stations, that meant they could increase wing production by a factor of 10. without hiring a single additional worker or expanding facilities. Wings were the critical bottleneck holding everything back. Fuselages were assembling faster than they could be mated to completed wings. Tail sections were stacking up in storage, waiting for completed aircraft to attach them to. The entire production line was constrained by wing assembly speed alone. Fix that bottleneck, and everything else would flow smoothly. Murray made the call that morning despite Eccles's screaming objections, over protests from the entire engineering department, over dire warnings from Boeing's legal team about liability if wings failed in combat and killed crews. Murray ordered the new rivet pattern implemented across all production lines effective February 25, 1942. He gave Frank Szymanski a $40 weekly raise and the impressive title of Production Methods Specialist. He gave Hendricks a promotion to senior supervisor. He told Douglas his job was safe for now, and he told Eccles that if he didn't like it, he could personally explain to General Arnold why Boeing was still building only 14 bombers monthly when the country needed thousands. The results were absolutely staggering when they came in. In March 1942, Boeing Seattle delivered 47 B-17s. In April, 91 aircraft. By June, they hit 186 bombers delivered. But the real explosion came in July, when all 42 wing stations were fully converted to Frank's pattern, and workers had completely mastered the new sequence through practice. July production 284 B-17s. August 319, September 362 bombers rolled off the production line in a single month. That was more than Boeing's entire 1941 annual production combined. The impact on the air war was immediate and devastating for the Luftwaffe. In October 1942, the 8th Air Force flew its first mission with over 100 bombers hitting industrial targets in Lille, France. The Luftwaffe had been built to fight defensive battles against raids of 20 or 30 bombers at most. They could swarm those small formations, pick off stragglers, make every mission costly enough to be unsustainable. But 100 bombers changed everything about air combat. The defensive fire from that many B-17s created overlapping fields of fire that made fighter attacks suicidal for German pilots. They called it the Wall of Lead because that's what it felt like. They'd lose 3 fighters to shoot down 1 bomber, and the Americans just kept coming day after day. By January 1943, the 8th Air Force was flying missions with 300 bombers regularly. By summer of 1943, 500 bombers in a single raid. Each one of those aircraft represented 2 hours of riveting time instead of 20 hours using the old method. Each one carried 4,000 pounds of bombs deeper into Germany than Hitler thought possible when he started the war. The Schweinfurt-Regensburg missions in August 1943, the raids that crippled German ball-bearing production, required 376 B-17s in the air. Without Frank's pattern, Boeing wouldn't have built that many bombers total by August 1943 at the old production rate. The entire strategic bombing campaign, the effort that drew German fighters away from the Eastern Front and forced the Luftwaffe into an unsustainable war of attrition, depended completely on Boeing's ability to flood the sky with flying fortresses. Boeing Seattle wasn't the only factory using Frank's pattern for production. By April 1943, Boeing Wichita, Douglas Long Beach, and Lockheed Vega had all adopted variants of it for their assembly lines. Combined production across all facilities hit 512 heavy bombers in a single month, an unthinkable number a year earlier. The Germans were producing about 1,000 fighters monthly to counter them at enormous cost. But it didn't matter anymore. You can't win an air war when the enemy builds bombers faster than you can possibly shoot them down. Frank Szymanski never became famous despite changing everything. He received a War Production Board commendation in July 1943, a certificate signed by someone he'd never met. It hung in his daughter's bedroom until she moved out in 1959, and probably got thrown away. Boeing gave him that raise and the fancy title of Production Methods Specialist. But after the war ended and production wound down, those specialist positions were quietly eliminated in the 1946 workforce reduction. Frank went back to Detroit, worked at Ford for 23 years doing similar work, and died in 1971. He never knew that his rivet pattern had fundamentally changed how aircraft were manufactured worldwide, because it did change everything, not immediately and not obviously. But the principle Frank stumbled onto became industry doctrine. In 1947, when Boeing began designing the B-47 Stratojet, their first swept-wing jet bomber, engineers didn't start with theoretical rivet patterns calculated in isolation. They started by consulting with assembly line workers about access points and actual workflow on the floor. The B-47's wing used a pattern that looked chaotic on paper, but could be riveted by 6 workers simultaneously in 3 hours. Nobody called it the Szymanski method officially. Nobody even knew there was a Szymanski behind it. They just knew that matching rivet patterns to assembly reality, instead of pure structural theory, produced better aircraft faster and cheaper. Douglas Aircraft applied the same fundamental principle to the DC-8 in the late 1950s. Lockheed used it for the C-130 Hercules military transport. When Boeing designed the 747, their first commercial jetliner, the engineering team included assembly line supervisors in the initial design reviews from day one. Revolutionary concept at the time. Ask the people who will actually build the thing whether the design is even buildable efficiently. The 747's fuselage panels used what Boeing internally called cluster riveting, which was Frank's pattern with a corporate name attached. It cut 707 fuselage assembly time by 60% compared to the Stratocruiser it replaced on production lines. The real legacy showed up in modern aerospace manufacturing philosophy that students learn today. There's a principle called Design for Manufacturability, or DFM, that every aerospace engineer learns in school now. It says that a design's elegance is measured not just by its performance, but by how efficiently it can actually be built by real people. The textbook example taught at MIT and Caltech and every aerospace engineering program in the world is B-17 wing riveting. How a theoretically optimal pattern proved inferior to a practically optimal pattern in real-world conditions. How assembly time reduction actually improved quality instead of degrading it like everyone assumed. Most students never learn about Frank Szymanski in those classes. They learn about Boeing's innovative production methodology development program as if it was a committee decision made by executives. Modern aircraft like the Boeing 787 Dreamliner take this principle even further with advanced technology. The 787's fuselage sections are joined with computer-designed fastener patterns that look completely random to the untrained eye, but they're optimized for robotic installation using sophisticated algorithms. Each pattern is generated by computers that consider structural loads, assembly access, thermal expansion, and 20 other variables simultaneously in complex calculations. Frank did essentially the same thing in 1942 with just a pencil and the back of a time card. He didn't have the mathematics to prove why it worked according to engineering theory. He had something potentially better than math. He had pattern recognition developed from watching thousands of rivets get installed and noticing what slowed everyone down in practice. That's the uncomfortable truth this story reveals about innovation and expertise. Frank wasn't smarter than Boeing's highly educated engineers. He wasn't better educated with advanced degrees. He didn't understand von Karman's stress equations or load path analysis from textbooks. What he had was different knowledge gained from experience. He knew how tired you get crouching in the same uncomfortable position for 40 minutes straight. He knew how pneumatic hoses tangle when workers cross paths constantly. He knew that theoretical perfection executed poorly produces worse results than theoretical imperfection executed flawlessly every single time. Boeing's engineers knew how to calculate stress distributions on paper. Frank knew how to actually build things with his hands. Both types of knowledge were absolutely essential for success. Only one type was valued by the organization. The aerospace industry eventually figured this out, but it took decades of painful lessons. Modern aircraft development uses integrated product teams where machinists and assemblers work alongside engineers from day one of design. When Airbus designed the A380, the largest passenger aircraft ever built, assembly line workers had veto power over design decisions that would make manufacturing impossible or inefficient, despite looking good on blueprints. That's Frank's real legacy in the industry, not the specific rivet pattern itself, which is obsolete now in an era of automated fastening systems and composite materials. The legacy is the idea that the person doing the work might understand the work better than the person who designed it in an office. That was revolutionary thinking in 1942 when hierarchies were rigid. It's supposed to be common sense now in modern organizations, except we keep forgetting this lesson and having to relearn it painfully every generation. Every innovation cycle produces its own Frank Szymanski somewhere. Someone who sees the obvious solution that experts are too educated to notice because it violates established theory. The smart organizations listen to those voices from the floor. The rest keep riveting wings in 20 hours while wondering why they're losing to competitors.